Okay, it's 5:30, so let's go ahead and get started today. As a good evening, everyone. How's everyone doing? So we're up to week 5 of our semester. Hopefully everyone's doing well. Okay, so the plan for today is that we're going to continue on with our lecture notes on beams. So hopefully we can either, at least make some significant progress on that or maybe finish it. And then after this, we have probably what we'll start on Wednesday is the last kind of big kind of chunk of lecture notes for this unit, which is on frame elements. Okay. And so today we're going to go over kind of two main topics for beams. Like first of all, how to compute reaction forces, and second of all, how to deal with distributed loads. Okay. Okay, so before we start, are there just any questions on just anything that we covered? I know we have a homework due tonight. So is there any questions on that I can answer before we get started? All right, so the question in the chat, thanks. All right, so the question in the chat is, so I wrote these huge nested for global systems together in the homework. Is there an easier way? So you're already kind of implementing a code to kind of solve these automatically. So you're jumping the gun a little bit. So it's nested for loops is kind of one way to do it. But actually, what I worked on actually at the end of last week and this weekend was kind of our first MATLAB activity, which I want to do next Wednesday, which is a MATLAB implementation of these guys. So it's actually up on Canvas right now if you want to take a very early sneak peek. But I would say kind of hold off on the MATLAB. We'll hold off on the MATLAB stuff until next week. Yeah. Mm-hmm. Okay. So there's no questions. Let's go ahead and get started. Oh, actually, let's talk about the midterm for a second. So we still have a couple weeks until the midterm, and so the midterm is planned for Wednesday of week 7. So that's 2 weeks from Wednesday. And so I think our discussion at the beginning of the semester, I kind of left you guys hanging a little bit on just the format of the exam and how the exam is going to work. And so after kind of a lot of thought and just also knowing that everyone's kind of dealing with a lot right now and everyone's schedule is still kind of crazy, I'm going to use the same policy that I used last semester with the virtual exam. So what I'm going to do is I'm going to upload an exam on Canvas. And then you guys will basically have 24 hours to do the exam and then upload it back to the website. So the only thing that I ask for you guys is that it's because it's virtual, you guys are welcome to use your notes and the lecture videos and basically any material that I've given you online. The only thing that I ask is that you guys please don't share any details about the exam until it's complete and everyone's basically turned it in. So that's basically the only thing that I ask for the exam. Okay? But we still have a couple weeks, and so I do plan on giving you guys one more homework before the exam, and that's going to be on the beams and the frame stuff. And then so you'll have basically the stuff from Ancestor 51, the stuff from this homework, and also the next homework after that for you to complete for the exam. Okay. Okay. So that's out of the way. Let's go ahead and dive into the lecture today. And so the first thing that I want to go over is how to compute reaction forces for beam elements. Okay. And so basically, when I say reaction forces, these are forces that are put onto the beam mostly by the constraints in order to make sure that the beam is in static equilibrium, right? And so every situation that we've covered so far is basically a static problem. And and just by the fact that we have forces and we have moments acting on these things, there needs to be some equal and opposite reaction forces from the constraints in order to make sure that our system doesn't move. And a lot of times computing these reaction forces is something that's important. Okay? And so the way that we can compute these for beams is actually quite simple. And so this is usually performed after you compute the displacements, okay, and rotations. Okay. And so basically after you assemble the system, apply the boundary conditions, and you plug in MATLAB and solve, you can basically take that same solution this displacement rotations and plug it back into your global system before you apply the boundary conditions. Okay? Okay. And so basically what you want to do is you want to plug the displacement solutions in at the step right after you assembled everything. Okay. And so in the previous example, we had that 6x6 system where we had the 12s and the 6Ls and all that stuff. I'm not going to write it down again because it would take a while. But then what you would do is after you compute your U and your thetas, you just plug that back into the system in order to compute your forces. Because most of the time, our global system looks like this, where we have a stiffness system, global stiffness matrix K, right? We have our displacements and rotations. So this is going to be our solution vector U. And then this is equal to a forcing vector F. And so by plugging our solution U back into the system, and we just perform the matrix multiplications with K, what we can solve for is F, where F right here contains the nodal forces and the nodal moments at every node in our system. Okay. And so I'll do an example next with some numbers just so you can kind of see that. Okay. But first, are there any questions on this? Okay. Okay, so a couple kind of notes just to kind of give you some sanity checks when you're computing these forces. Okay, and so remember these reaction forces should be these are the forces that constraints like a roller constraint, like a pin constraint, like a fixed constraint. These are the forces and the moments that are applied from the constraints on the structure. And so when you're computing these reaction forces, it makes sense that the only places where you would have non-zero forces and non-zero moments are the degrees of freedom that are constrained. Okay. Okay. And so in our particular case, it's basically only the places where the displacement is forced to be zero. Okay. But there's one exception for this, and the exception is that you'll also get a non-zero reaction force on the nodes where a Neumann condition is applied. Okay. And in that particular case, the reaction force that you compute should be equal in magnitude and sign as whatever load that you were applying to begin with. Okay. And so basically, when you're computing these reaction forces, you should only get non-zero reactions where you apply boundary conditions. Okay? And that's why we have to do this on the system before we apply the boundary conditions. So if we do it on the system with the boundary conditions, we just kind of get our system back again. So that's why we have to do it on these ones. Okay. And so for the nodes where there's no boundary condition, there's no Dirichlet, no Neumann, when you compute your reaction forces, you should get zero for that. Okay. So this is kind of I mentioned this just because this is kind of a good sanity check that you can do, after you compute your reactions, just to make sure that everything is kind of, working out well. Okay. And so if these sanity checks aren't satisfied, then probably you might have to go back and check and see if, you either computed the displacements wrong, you set the problem up wrong, or, something might have gone wrong in the process on which to get here. Okay. Okay. And so with that out of the way, let's go ahead and work on an example. And so let's say we have a two beam system. Okay. So let's say we have beam A and beam B, right? And these guys are identical. And so they both have a length of 3 meters. Okay. And then let's put in the material properties. So we have a Young's modulus of 210 gigapascals. We have a moment of inertia of 2 times 10 to the minus 4 meters to the fourth. Okay. And then just to show you guys that you can, that what we're doing this time with beams is, you can combine the stuff with our trusses. Let's throw a beam in here just for, or let's throw a spring in here just for fun. Okay. And so let's say that the right side of this beam here is supported by a spring. Okay. And this will be element C. And the spring constant for the spring is going to be 200 kilonewtons per meter. Okay. Right. And so let's label the nodes. And so let's call this guy node 1. We'll call this guy node 2. We'll call this guy node 3. And then we'll call this guy node 4. Okay. We got the watermelon color scheme coming on right now. Okay. And then to force this system, we have a downward force of 50 kilonewtons. And that's going to be applied here. Okay. So we have P equals 50 kilonewtons. Okay. And so from this system, what we want to solve for, just like we always do, is we want to solve for the nodal displacements or and nodal rotations. Okay. And since we just talked about it, let's solve for the reaction forces as well. Okay. And so, this might seem like we're throwing a wrench in there with the spring, but it's, you'll see it's not that big a deal. Okay. All right. Any questions on the problem setup? Okay. Okay. So let's start this problem just like we always do. So let's start with the element stiffness matrices. Okay. And so let's start with our two beams. And so our two beams are just very classical beams. So we can just plug and chug our beam element stiffness matrix. Right? So let's start with A. So A is going to be EI all over L cubed. Okay. And this is going to be equal to our 4x4. So this is going to be 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, 4L squared. Okay. And then let's specify the nodes that this guy works on. So element A is on the left of our system. So this is going to work on nodes 1 and 2. Okay. And so that's going to be U1Y, theta 1, U2Y, and theta 2. Okay. So that's the element stiffness for element A. And so let's look at element B. Right, so element B is also a beam, and so it's going to have the same matrix. So I'm not going to rewrite the whole thing. Okay, so just imagine that this is the same, and then let's write out the node that it works on. So this one works on nodes 2 and 3, and so we're going to have U2y, theta 2, U3y, and theta 3. Okay, and then finally let's have element C, and so element C is simply just a spring. It's a vertical spring, so you can write this in the global or in the stationary coordinates with theta is equal to 270 in this case, because the lower node is on top, and so we have to rotate all the way around. Or if you just notice that because it's something at a 90-degree angle, we can just write our 2x2 element stiffness and just have them work on the appropriate nodes. So our 2x2 element stiffness can be K minus K minus K K. and then U3Y, U4Y, okay? Because the axial direction of the spring aligns perfectly with the Y direction right here. So we can just state it just like that, okay? Okay, any questions on this? Okay. And so at this point, you can probably go in and express, everything or plug in numbers just so you'll have the numbers there. Or you can kind of wait to the end. That's good too, right? And so at this point, now that we have the element stiffness matrices, we can assemble them into the global matrix. Okay. And so our global system will look like this. So we have EI over L cubed, okay? Okay. And so since this is kind of a weird system because we have the spring there. So normally, this the size of our global stiffness matrix is a multiple of 2. But in this case, because we have the spring, we have U4Y, which is kind of the axial displacement at node 4 right here. Okay. But there's no rotation there because it's a spring, and a spring doesn't support any rotation. Okay. And so that's why we have this kind of weird 7x7 matrix right here. Okay, so I'm not going to fill everything in because I think that would take a little bit too long. But I'll at least show you the places or the locations where to insert the element stiffness matrices. Okay. And so let's start with the element A. So remember, element A works on U1Y and theta 1. Okay. And so it would go into that location right there. Okay. Next, let's do element B. So remember, element B works on the displacements on node 2 and node 3. Okay. And so element B would go something like that. So it would be into a 4x4 chunk there. And then finally, we have element C, which I'll do in purple right here. And remember, element C only works on, the axial component. So we're actually going to skip over the rotation and then just have element C's element stiffness matrix going into these 4 spots right here. Okay. Okay. And so the only thing that you would have to look out for in this case is to kind of remember that we have this EI over L cubed in front. Okay. Because normally when we put the element stiffness matrix for spring, we just put K, right? But in this case, since we have that factor out in front, we need to account for that. So the things that we're actually inserting here for element C are going to be K multiplied by the inverse of this factor right here, just to make sure that it works out. Okay. And so at that location, we have KL cubed over EI, and that's the same for this location right here. And then for these locations here, we have a minus KL cubed over EI, okay? And so when you're doing these problems with kind of the multiple different element types, you have to remember what your factor in front is. And if you're adding different elements in there, make sure you account for that factor just to make sure everything is okay, okay? And so when we multiply the frontal factor by these guys, the EI over L cubed is going to cancel out with this EI over L cubed there, so that we just end up with K, okay? It's a subtle thing that that I forget half the time too, but it's something that's good to remember. Okay. Any questions on the global stiffness matrix? Okay. And so just like we have in the past, now that we have this global stiffness matrix, our next step is to apply boundary conditions. Okay. And so in this particular case, we have 2 boundary conditions. So we have a fixed boundary condition on the left-hand side at node 1. So that's going to knock out both U1Y and U0. or theta 1, I'm sorry. Okay. And then we also have a fixed support at the bottom of the spring, and so that's going to make u4y is equal to 0. Okay. All right, so these guys form our Dirichlet boundary conditions because these are our constraints. Right. And then we also have one Neumann condition, and that's going to be applied on the row for u3y because it's a downward force on node number 3. Okay. All right, any questions on this? Okay. And so if we plug in all those things and we apply the boundary conditions and all the loads and everything, what we'll get is the following. So here's our solution. Okay, so first of all, we get u1y and theta 1. These guys are going to be equal to 0 because of our fixed condition over there. Okay. Next, we have u2y and theta 2. Right, so u2y is going to be a minus 0.02 meters, and theta 2 is going to be a minus 0.012 radians. Okay. Right, next we have u3y, so u3y is going to be a minus 0.0638 meters. Okay. Next we have theta 3, and theta 3 is going to be a minus 0.016 radians. Okay. And then finally we have u4y, which is going to be 0. Okay. All right, so the question is EI over L related to the moment? And so it's actually a factor that gets multiplied by the entire thing. So that comes out kind of directly from the beam equations. And so this is just kind of the standard form for the element stiffness matrix for beam. And so it does partially have to do with the moments, but also the transverse displacements have a similar factor there as well. Yeah, so it comes just kind of straight out of the equations that we use to form the matrix. Right? And so these are our displacement solutions, or deformations. Okay. And so now that we have the deformations, we can plug this back in to our global stiffness matrix in order to find the reaction forces. Okay. All right. And so I'll actually write out the full system for you guys on the next page. But are there any questions on just how we got these solutions and the next step? The phrase before BC looks funny because BC kind of already stands for before Christ. So like before Christ would be like before the birth of the universe, I guess. Okay. And so let's go ahead and plug this guys back in. So before we plugged in our boundary conditions, so this is the thing that I didn't want to write before, but I guess there's no escaping it. Okay. And so before we applied the boundary conditions, we had something that looks like this. So we had 12, 6L minus 12, 0, 0, 0. Oh, one more 6L. We're missing something. Okay. And this is, remember, U1Y, theta 1, U2Y, theta 2, U3Y, theta 3, and U4Y. Okay. we can draw in the corresponding matrix here. So we have U1y, theta 1, U2y, theta 2, U3y, theta 3, and U4y. Okay. All right, so that's the second row. Okay, that's the third row. Sorry, this is L squared. There ain't no L cubed in here. Okay, so in this slot right here, we have to add our spring, right? So this is K over KL cubed over EI. Okay. There was already something else there, so we have to add that guy. Okay, and in that last column, we have a minus KL cubed over EI. Okay. Okay. And again, you know, this is all in the lecture notes. So if you you know, you don't want to write this down right now, then you know, definitely you can just refer to that. Okay, so here's our global system 7 by 7 before we applied the boundary conditions. Okay, and so one thing that you can check to make sure that this is the right matrix that you're plugging into is remember that our global stiffness matrix is always symmetric before we apply boundary conditions. Okay. And so we, you know, obviously, you know, we have everything in the matrix portion. We have everything in this vector now because we had just solved for it. And so all we got to do is just perform the matrix multiplication, which, you know, of course you can do in MATLAB because it does that easily for you. Okay. And then for your solution, you know, this is what you get. So we get F1y. I don't know why this always does this. Okay. We have F1y is equal to 37.23 kilonewtons. Okay. We have M1. M1 is equal to minus 893. Minus 893.62 kilonewton meters. Right. We have F2y. This is equal to 0 newtons. That's 0 newtons, not on. Okay. M2 is equal to 0 Newton meters. F3y is equal to minus 50 kilonewtons. M3 is equal to 0. Okay. And then we have F4y is equal to 12.77 kilonewtons. Okay. Okay. And so before we move on, let's do sanity check. Okay. Oh, there's a question in the chat. Symmetry A is equal to. Yeah, I think there's a way to check it in MATLAB. I'm not sure the exact syntax, but there is a way that you can check that a matrix is symmetric. Yeah. You might not get exactly that in MATLAB because there's always, like, you know, numerical error. So, you know, just kind of be a little bit careful using that command with, like, lots of numbers like this. Yeah. Okay, so let's do a sanity check real quick. So first, let's check the nodes. Let's check all the non-zero values here. And so we have a non-zero value here, 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 and here, right? And if you look, if we check back on the diagram, you know, our diagram looked like this, right? And so we had a fixed support on node 1, a fixed support on node 4, and a Neumann boundary condition on the y component of node 3. And so basically both degrees of freedom in node 1 should be 0, or should have a reaction force. The displacement boundary, or the force on node 4 should also have a non-zero value, and the force on node 3 should also be non-zero. Okay, and so we go back to our solution for the reaction forces. We see that's exactly the point here. So we got, you know, a non-zero force and a non-zero moment at node 1 where it's fixed. We have a non-zero force on node 3, and in particular, it's exactly the same value as the force that we're applying, and so that matches up with the Neumann boundary condition. And then finally, we also have a non-zero force at node 4, which is where our, you know, where our other fixed boundary condition is. Okay? And so all the other reaction forces here are 0 because those nodes are free to move. Okay? All right, any questions on this? So reaction forces, you know, it's not that big a deal. You know, most of the times you already have everything already. You already have the matrix, and all you got to do is just multiply again by the whatever deformation that you found in order to solve for the reaction forces. Okay. Okay. And so that's how you do reaction forces in beams. And so let's move on to the last topic for our beams lecture notes, which is this idea of distributed loading. Okay. And so up until this point, you know, whenever we placed a force or a moment on something, those always occurred strictly at just the nodes, right? And so, you know, these are probably the most convenient that we can use for our calculations, but this isn't always what's reflective of reality, right? And so if we think back even to just our first ANSYS example, right? So in our first ANSYS activity, what we did was we applied a pressure force on the right side of the plate. And so that pressure is not a discrete force that's being applied at the nodes, but it's a force that's distributed over the entire right side of the plate. And so distributed forces are actually pretty common in reality. And so let's say one common example is like, say you're designing a bridge, right? And so the way that you can represent the force of the cars that are sitting on the bridge, you know, you can say that the force of the cars is distributed evenly across the bridge. Or if you're designing like a large building, right? So when you're designing a large building, you have a wind that's blowing against the building all the time. And so that wind doesn't just express a force in just one discrete point. It distributes that force over the entire, you know, surface, or, you know, one of the surfaces of the building. And so distributed forcing is pretty common. And so in order to basically work with it within the framework of the problems that we've been doing, we need a way to convert a distributed force into discrete nodal forces. Okay? And so let me draw a figure first. Okay? And so a distributed force would look something like this. And so let's say that we have a simply supported beam. Okay. Normally, when we would have a force, we would have them be applied at our nodes right here. Okay. But a distributed force would look something like this. Okay. And so it would be a force that would be evenly distributed all throughout the beam. Okay. And so in order to work with these and be able to solve finite element problems with these distributed forces, at least with the direct stiffness method, what we need to do is we need to convert these distributed loads into discrete nodal loads. Okay. Because once we have them convert into discrete nodal loads, we can just treat them exactly the same as what we did before and just do our regular process. Okay. Okay. And so the principle that we're going to use to do this, right? And you know, whenever you're converting a distributed force into a nodal force, what you want to do is you want to make sure that these forces are equivalent. Okay? So in other words, they produce the exact same displacements, the exact same rotations, the exact same reaction forces as if it was the distributed load. Okay. And so there's lots of different notions of equivalence, throughout the applied physics literature. But the one that we're going to apply for this one is the concept of work equivalence. Okay. And so let's remind ourselves what the definition of work is. So probably like all of you, when they released Hamilton on Disney Plus, I watched it with with my friends. So whenever I say work, I think of that song that they sing in the middle of it, or near the beginning or something, right? But we have a different definition of work. It's kind of like this is actual real work, so it's not really virtual work. So we'll come back to virtual work once we do kind of element stiffness matrices after the midterm. But this is actual work right here. Okay, so the work is it's a unit of energy, and so in particular, it's the energy that is exerted by a force acting on an object over a certain distance. Okay. And so basically, the formula for this is kind of in the most simplistic sense. Probably what you learned in your physics classes was work was equal to force times distance. Okay. And so we're going to apply this this concept in order to compute equivalent nodal loads for a distributed load. Okay. All right, so before I turn the page, let me give a function for this. And so usually a distributed load has we'll give it the symbol W of x, and then this has units of force per length. Okay. Okay. So no, those of you who might have taken me for finite elements before, Wx, it means another thing that we'll come back to after the midterm. But this is a different Wx. So this Wx is a distributed load, so it has nothing to do with weighting functions yet. And so we'll do that kind of after the midterm. But for now, W of x is just a force divided by length. Okay. Any questions on this before I turn the page? Okay. Okay. And so the way that we can compute work is basically is to do kind of the same thing. And so we take a force and we multiply it by the distance on which it's acting. Okay? And so for a distributed load, because we have a load that's kind of distributed and it can be kind of any weird function, the way that we're going to compute work is we're going to integrate. Okay? Okay? And so I'll give it the symbol W sub dist. Okay? And this is going to be the integral from 0 to L of our distributed load function multiplied by our displacement function through the beam, dx. Okay? And so this is our distributed load. Okay? And this right here is our displacement function. Okay? And so basically what that represents, this uy of x, basically represents the transverse displacement of the beam as a function of x. So as we go through the beam, the y deflection is either going to go up or down depending on the loading, and that function describes that. And so this is kind of one side of our equation. Right? So I'll come back to this equation because there's kind of still a lot that we don't know in this equation yet, mostly the uy of x. Okay? But basically the concept of equivalent work means is basically stating that if we replace this beam with a beam that looks like this, okay? And so if we replace a beam where we have a force over here, we'll call this F1y, a force over here, we'll call this F2y, okay? Where over here, this is node 1, over here is node 2. In addition to this, we have a moment over here called M1, and a moment over here we'll call it M2, okay? And so if we, basically what we have right here is a beam with nodal loads, so these are kind of the ones that we're accustomed to solving in our problems, okay? If we compute the work for this problem, okay, it'll basically be the product or the sum of the of all of these forces and moments multiplied by their respective deformation. Okay, and so basically what we're going to say is that the work done by F1y is going to be F1y my stylus kind of keeps doing weird stuff. Okay, F1y multiplied by the displacement at that node. Okay, so we have F1y multiplied by U1y. Okay, so remember that's the nodal displacement U1 that we're going to solve in our finite element context. Okay. Same thing for F2y. So F2y is going to be multiplied by the displacement at that location. Okay, so that's going to be U2y. And so to that, we're going to add the work done by the moment. So the work done by a moment is the moment or the torque multiplied by the rotation, so theta 1. So that's going to be M1 theta 1. And then to that, we're going to add the work done by the second torque, M2. So that's M2 theta 2. Okay. And so what the concept of work equivalence states is that these two should be equal. And so what we're going to do eventually is we're going to take these two expressions for work, set them equal to each other, and then use that to solve for all of these guys. Okay. Right? Because if we can work through the algebra and a little bit of the calculus here and solve for F1y, F2y, M1, M2, and then what we can do is we can replace our distributed load with these nodal loads, and we can solve our finite element problems the same ways that we did before. Okay. All right, any questions on this? Okay. Okay. And so how are we going to do that? So we know that everything on the right, everything for the nodal loads, we'll assume that, you know, that's basically kind of the end form of this. So we're not really going to touch this guy at all, right? And so what we want to do is we want to work on the other side of the equation up here given by this integral. Okay. And so let's start with w of x. Okay. And so w of x, remember, this is our mode function. And so 99% of the time, this is going to be something that's given to you. And so just based on the physical situation that you're presented with, or for this class, just based on just whatever I tell you, you know, w of x will be given to you. So this is usually going to be known. Okay. And so if that's known, then that's fine. And so we can, you know, leave that guy alone. And so the other part of this equation is this uy of x right here. And so this uy of x might look a little bit strange to you because, you know, we haven't been solving anything in terms of function of x. Everything that we've been solving for are just, you know, solutions at the nodes of our finite element system. And so we don't actually have a function of x. What we have are these guys, right? So we have the nodal solutions u1y and u2, right? And so the question is, how do we take a nodal solution like this and turn it into an analog function of x? Okay. And so the answer to that question is that you know, we have to assume a functional form for uy of x. And actually, you know, this is something that I've kind of been skipping, not only for this unit, but also for the other ones, is that usually when you form an element stiffness matrix like we have before we get to that point, the book kind of had to assume that we knew something about the solution, or that the solution took you know, a certain form. And so this will become a lot more prominent after the midterm when we do kind of more general finite elements. But for here, you know, it wasn't. You know, I kind of wanted to focus more on just kind of the process more than the derivations, and so I've kind of left that alone. But just for this kind of application, we need to kind of dive into that a little bit. So it'll be kind of a nice segue into the stuff after the midterm, and you know, it's not going to be as intense as before. Okay. And so let's assume a form. Okay. Okay. And so how do we go about doing this? And so because when I say form, that means kind of a general kind of functional class. So that could be anything from like a sinusoid, it can be a polynomial, it can be just a constant function. So how do we choose? Because there's you know, literally, you know, hundreds of different functions that we can choose for this guy. And so the way that we usually choose this or assume is we first look at our governing equations. And so for a beam, if you remember, it was this guy that looked like this. We had E times I times d to the fourth of uy times dx to the fourth, okay, is equal to 0. Okay. And so this is kind of our starting point. And so what we can say from this is that whatever we assume, or you know, what we assume for our functional form has to satisfy this equation. Okay. And so kind of a simple function that can satisfy this is a cubic function. So a cubic function, what I mean by that, it's a polynomial where the highest order term has an order 3. Okay? And so if we write out this form, it would look like this. Okay? And so kind of the most generic form for a cubic polynomial looks like this. We have a0, where a0 here is just a constant, okay, plus a1x plus a2x squared plus a3x cubed. Okay. And so in this equation, these a's right here, these are arbitrary unknown constants. Okay. So we don't know them yet. So it's but basically this form right here is just the general form for a cubic polynomial. So actually, if you plug this guy into this equation up here, okay, and then what you'll see is that this satisfies this equation. So you know, if you take this function and you take 4 derivatives of it, then basically every single term will cancel out, and then what you get is 0 equals 0, which means that this equation is satisfied. So we don't have any kind of extra terms that that are floating around here. Okay. And so this equation right here, this is kind of the starting point for us to plug into our kind of our principle of equivalent work. Okay? Okay. And so if you remember back in our work equation, we had this this function right here, uy of x. And so that's exactly what we have right here. So we have a uy of x. Okay? And so we can plug this guy back in. The only problem is that we don't know what all the a constants are. So we don't know what a0, a1, a2, and a3. And so what I'm going to do on the next page is basically give you conditions on how to solve for these constants. Okay, any questions on this? Okay. Okay, and so how do we solve for the A's? Okay. And so the ways that we're going to solve for the A constants is to basically require that this assumed function matches our nodal solutions. Okay. Cat's hungry. Because remember, what this assumed function is supposed to represent is kind of an assumed form for our finite element solution. And so if it's supposed to represent kind of the same solution, it should still match the same guys. Okay, so let me draw our beam again. Okay, and so remember, our beam has the following displacements at the nodes. Okay, and so at node number 1 right here, we have a vertical displacement u1y. And then at node number 2, we also have a vertical displacement of u2y. Okay. We have a rotation θ1, and we have a rotation θ2. Okay. And so what we can basically do from this is we can basically require that all of our basically require that our assumed solution matches these guys. Okay. And so if we consider this to be x is equal to 0 for a second, and we consider this over here to be x equal L. Okay. So the four basically equations that we're going to solve for is that uy, which is our assumed function, and we evaluate that at x is equal to 0. This is going to be equal to u1y. Okay. And the same token, if we apply uy, and we apply x is equal to L, this has to equal to u2y. Okay. And so remember, those are our nodal solutions for the displacement at those nodes. Okay. And so next, now we have to apply the rotations. Okay. So we have duy dx, and so we basically just take our assumed solution. We just take the derivative once with respect to x. If we apply this at x is equal to 0, okay, this should equal to θ1. Because remember, we're assuming that our rotations are small, and so that we can relate the displacements and the transverse deformations by this formula. Okay. And by a similar token, if we take the derivative of uy, and then we evaluate it at x equal to L, and we set that equal to θ2, then this gives us one more equation. Okay. And so from these, we can solve for A0, A1, A2, and A3, because it's basically going to give us 4 equations in 4 nodes. Okay. So I'm not going to work through all the algebra for this because it's kind of a lot, but I'll give you kind of the end result, which is what we're going to need for our virtual work, or equivalent work principle. Okay. But does this kind of make sense on on the constraints that we put on our assumed solution and why it has to be these conditions here? Okay. Okay, so you apply those 4 conditions. You do algebra for like an hour, and then you end up with this. Okay. And so our ending function for uy of x, okay, looks like this. So it's a doozy. So buckle up. Okay. And so first we have a term 2 over L cubed multiplied by the quantity U1y minus U2y, okay, plus 1 over L cubed multiplied by theta 1 plus theta 2, okay, and this is multiplied by x cubed, and so that's our cubic term right there, okay, plus minus 3 over L squared times U1y minus U2y what minus 1 over L 2 theta 1 plus theta 2. Okay, this is our quadratic term, so all that's going to be multiplied by x squared plus theta 1 x plus u1 y. Okay. So this kind of monstrosity of an equation is what you get by applying those 4 conditions on our assumed solution. Okay. And so just by going off this, we can see that this guy right here, this is our A3. Okay. This guy was our A2. This guy was our A1. And obviously this guy is our A0. Okay. And so you can see, you know, it's quite a lot of algebra to kind of get to this point. So, you know, definitely, you know, if you're up to it, I would verify this on your own. But you know, it's not required. Okay. Okay. And so now that we have this equation, we can plug this back into our original work equivalent form and use that to solve for the nodal loads. Okay. But I'll just make a quick note, because this is, you know, do you remember when we first started talking about our beams, I said there was a lot of steps that I skipped on deriving the element stiffness matrix. And so if you're curious about those steps, this is basically what you would do. Okay. And so now that you have this expression here for uy of x, in order to solve for the beam element stiffness matrix, you can basically plug this into the force displacement relationships. Okay. And so our force displacement relationships look like this, right? And so these are the equations that I introduced before. Okay. And so if you take this solution for uy of x, plug these into these, okay? And then if you evaluate these at the endpoints of the beam, okay? And so our endpoints, remember, are x is equal to 0 and x is equal to L, okay? And so you have 2 equations at each of the 2 nodes of our beam, so that will give you 4 equations, okay? And then what this will do is this will give you 4 algebraic equations, which will form the basis for your element stiffness matrix. Okay. And so, you know, if you wanted to do that on your own, that's kind of a good thing to do, because then you can kind of see exactly how we got those equations as we did. Because we kind of did that, you know, for the spring and for the truss, but I skipped this step for the beam because it's a little bit quite involved. But if you want to run through that same process, this is basically how you would do it. So you would take this function, plug it into these force displacement relationships, get an algebraic equation, and plug that back into the and have those become your equations for the element stiffness. Okay. Okay. Any questions on this? Okay. And so we have, you know, might seem like quite a detour, but basically we have everything that we need now in order to compute our equivalent nodal loads. And so let's do an example to see how this is done. And so so the example that they do in the book actually is just a constant function, which is, in my opinion, not that helpful. And so I wanted to give you guys a function of an example of something that's a little bit complex. Okay, but it's not that complex. It's really just one step up from a linear function. Okay. And so let's say that we have a situation where we have a beam. Okay, so it's simply supported, and we're going to apply a distributed load over it. Okay, so a distributed load W of x. And then let's say that it's, instead of a constant function, let's say that it's a linear function. And in fact, it's linear ramp. Okay? So it's going to look like this. Okay. So in fact, you know, we actually know the actual function. And so our actual function will look like this. So W of x will equal to 5,000 x newtons per meter. Okay. And so what we want to do from this problem is we want to compute the equivalent nodal loads at endpoints 1 and 2. Okay. And so we have our endpoints 1 and 2, and we want to compute equivalent nodal loads. Okay. And so we're going to use the principle of work equivalence and basically compute the load, the discrete nodes F1, Y, F2, Y, M1, and M2. That's going to be exactly equivalent to this distributed load right here. Okay. All right. Any questions on the problem setup? Okay. So let's go about doing it. All right, so remember, we're using the principle of work equivalence. Okay. And so the principle of work equivalence basically says that the work done by the distributed load has to be the same as the work done by the nodal loads. Okay. And so what we have for the distributed load, remember, we have W of x right? W of x multiplied by uy of x dx. Okay. And where W of x is given by 5,000 x above, and then uy of x is given by that monstrosity of an expression on the previous slide. Okay. And so this has to be equal to the nodal loads, or the work done by the nodal loads. This can be F1y, U1y, plus F2y, U2y, plus M1 theta 1, plus M2 theta 2. Okay. And so just like we talked about before, our focus is mostly going to be on the left side of this expression right here. And so in order to evaluate this, we're going to plug in. Okay. Plug in for W of x and uy of x. Okay. Then integrate. Okay. So it's about to get, you know, quite messy. So, you know, before we kind of dive into that, are there any questions on this? Okay. So let's go ahead and get rolling. So remember, our W of x here is 5,000 x. And so just to kind of save us just a lot of multiplying, I'm going to take the 5,000 and pull it out. Okay, so we're going to have a 5,000. Okay. Integral from 0 to L. Okay. And then what I'm going to do is I'm going to take that x from 5,000 x and distribute it to every single term in uy. Okay. And so remember, our uy of x is given by this expression right here. Okay. And so we have a, let's see, we have a 2L cubed times u1y minus u2y plus 1 over L cubed multiplied by theta 1 plus theta 2. Okay. And this is all multiplied by x cubed normally in our just uy, but we multiply by one more x from w of x, and we get x to the fourth. Okay. And so that's our first term. And so our next term is minus 3 over L squared u1y minus u2y, okay, minus 1 over L 2 theta 1 plus theta 2 x cubed, okay, plus theta 1 x squared plus u1 x dx. Okay. All right. So I just took our expression for u1y and I just multiplied 5,000x by everything, but I pulled 5,000 out in the front. Okay. All right. So the question is, can we always use that uy function regardless of how the distributed mode looks like? Yes, that's correct. So this this function uy of x that we kind of sort of derived on the previous page, that's valid for any beam. And so no matter what the distributed mode looks like, you can use that ui for any of those. And so what's going to be different for the different distributed loads is that w of x function. So depending on the interaction between w of x and uy of x, then you're going to get different loads, but the ui is always going to be the same. Okay. Yes, thank you. It should be dx, not dy. Okay, and so let's take this guy and let's integrate. Okay, and so after performing the integral, then we have, just for kind of simplicity, let's assume that L is equal to 1. Okay. And so if we perform the integral, then we end up with this guy. Okay. So we have the same 2 over L cubed times u1y minus u2y plus 1 over L cubed, or L squared, sorry. This should be L squared, times theta 1 plus theta 2. Okay. And all this is multiplied by x to the 5th over 5. Okay. So I just integrated that x to the 4th term. Okay. And then to this, we're going to add minus 3 over L squared times u1y minus u2y. Okay. And 80 bucks on this stylus, and sometimes it's a piece of crap. Okay, subtract minus 1 over L times 2 theta 1 plus theta 2. Just theta 2, not 2 theta 2. Okay, and all this is multiplied by x to the 4th over 4. Okay, plus theta 1 x cubed over 3 plus u1y x squared all over 2. What the heck? Huh. Hang on. My note-taking app froze. Technical difficulties. Okay, there we go. X squared divided by 2. Okay. Right, and then all this is evaluated from 0 to 1. Okay. Okay. And so now at this point, we can evaluate the bounds. which in this case is fairly simple just because, you know, our bounds are just from 0 to 1. And so we're just going to plug in 1 for everywhere that we see x. We're going to plug it for L too. Okay. So I know I kind of, you know, dropped it halfway. So I want to give people just a few minutes just to catch up. Okay. But while people are catching up, are there any questions on this? Okay. Maybe we'll give them like 30 more seconds. Yeah, so again, you know, all this is also in the notes. So, you know, if you want to just follow along there, that might be good because it's just a lot of algebra. And I just, you know, I don't want you guys to get too caught up in the details, but, you know, I just want you to kind of see that this is kind of the process that you would follow in order to compute the nodal modes. So, you know, the integration and the stuff and evaluating bounds, I know you guys can do that. And so, you know, if you just kind of want to follow along, that's okay too. Okay, and so let's evaluate the bounds. And so by evaluating the bounds, we get the following. Okay, so we have 5,000 on the outside. And so we have an L value of 1. And so what that gives us is just 2 multiplied by U1y minus U2y, okay, plus 1 over L squared times theta 1. Oh, sorry. No more L, so this is just 1 multiplied by theta 1 plus theta 2, okay? And this is multiplied by 1 over 5, okay? Plus minus 3 over L squared, which is just 3 now, minus 3 times U1y minus U2y, okay? Minus 1 over L, which was just 1 now, so 2 times theta 1 plus theta 2, okay? And all this is multiplied by 1/4 plus theta 1 over 3 plus U1y all over 2. Okay. Okay. And so at this point, you know, we're getting close. And so what we want to do now is we want to distribute everything and then group the terms according to U1y, theta 1, U2y, and theta 2. Okay. Okay. And so we're going to distribute that 5,000 all throughout. We're going to distribute the 1/5. Okay. And then what we get is the following. Right. Okay. And so what we get is, well, let me distribute the fractions first, and then we'll distribute the 5,000 at the end. Okay. And so what we get is 5,000 times 2/5 U1y minus 2/5 U2y plus 1/5 theta 1 plus 1/5 theta 2. Okay, so all that came up from the first term up there, minus 3/4 U1y plus 3/4 U2y, okay, minus 1/2 theta 1 plus 1/4 theta 2 plus 1/3 theta 1 plus 1/2 U1y. Okay. Okay. And so at this point, what we're going to do is we're going to distribute, or we're going to group the terms into basically a U1 term, a U2 term, a theta 1 term, theta 2. Okay. So let me kind of color code that because we're almost out of time, and I think we'll finish that next time. And so basically all the terms with U1y, we're going to group them together, Okay, so I'll circle those all in red. All the U2 terms, we're going to group those together. And so I circled those in green. All the theta 1 terms we're going to group together. And then all of the, these are different color, it's purple. All the theta 2 terms we're going to group together too. Okay. And so by grouping them together, what we're going to do is, what we're going to be able to do is we're going to basically be able to equate this with the work done by the nodal loads. Okay. But we're out of time, so we'll finish up just the last bits of this example next time. So there's really just a couple more steps, but I don't want to hold you guys any longer than this. So so that's all I got for today. So thank you guys, everyone, for tuning in, and I'll see you guys on Wednesday. If you have any more questions, I'll stick around for a while too. The 1/4 delta 2 should be negative. 1/4 theta 2. Yes, that should be negative. Thank you. Yep. Right. So so that's basically the last step. So once we get the coefficients for all of these, the color terms here, then those will basically be your discretized loads. Yeah. So we're like right at the end, but it's yeah. I've been running over on my lectures a bit, so I didn't want to do that again today. So we'll finish up that last bit next time. Yep.